algorithm. I originally had much more involved metaphor about quilting and so on, but I luckily abandoned that. That was a bit too much. So the left of this nice, it's sort of a logical landscape in some sense. Anyway, it's great to talk here. I've been a member of Samson's group for about 5 years. It goes fast. And it's been great having Samson down before and someone to talk to, learn from about lots of things that are of a lot of interest for me, but with quite different backgrounds, it means that there's always something I can learn. So anyway, I'm going to talk about a lot of things that Samson knows all about, and a lot of you know a lot about, and see how these things fit into what I think of as the logical landscape. Let me know if that's a good term. So I'm going to start with something you all know about very well, Cartesian categories. This is a slide on Cartesian notion of logic. So all the notions here are product and these are deeply important basic ideas that we're all extremely familiar with. We've been hearing about lots of things based on this extremely general foundation over the last couple of days, and I'm sure we will tomorrow as well. In particular, the lambda calculus has extremely significant impact on the relation to science. And Topos theory also is a foundation for logical mathematics. Very important. We've heard also about algebraic theories while we've been here. So this isn't supposed to tell you anything you don't know, but just to pick out this realm of ideas as being clearly closely connected, forming a cornerstone of the way we understand logic and model it. Okay, so let's move on. This is one of Samson's favourite pictures, which I truly stole, attempt for copyright papers with Rada. So trace monoidal categories are now moving away from this Cartesian paradigm. Trace monoidal categories are of interest when we're thinking about resource sensitive. Much of Samson's important work, including the paper from which this picture was taken, has been on categorical semantics and geometry of interaction, in particular description of how we can use trace monoidal categories to describe, to reason about coupling. So what's interesting here as we move from Cartesian logics towards these categorical ideas that are more suitable for linear logics is that geometrical ideas are starting to become important. So in particular, we have a picture here involving some lines and some loops. People very rarely draw similar pictures in the Cartesian case, but Martin gave us a conspicuous counterexample yesterday. Samson has also done a lot of related work, say, on temporal Lie algebras, which are strongly geometric relations, closely connected relations. And these things are tightly connected as well. A close connection between these Cartesian logics, given Cartesian logical setup. Often there are ways to extract from it linear logical setups. There are ways to move around this kind of thing. If we get even more geometrical, we move to compact categories. Something else that Samson along with Bob has done a lot of work on, showing how they provide important mathematical tools to reason about the foundations of quantum mechanics. So going back almost 10 years when Bob and Samson did this work, every other talk at a meeting like this would have all these sorts of pictures, but we've hardly actually seen any of them, which is quite strange so far this meeting. So here's a good one to remind ourselves of what this theoretical work looks like. So the idea about compact monoidal categories is that symmetrical monoidal categories are duals for objects. That's a mathematical definition. But what that really means is something completely graphical. It means for any diagram that we can draw involving one-dimensional manifolds, lines, which are allowed to be kinked, curves something like this. These lines are labelled by objects of our compact monoidal category, and also decorated by vertices, which correspond to morphic by simply referring to features of and commodity in one-dimensional. And the point of Samson and Bob's work in this context is to show that this gives an incredibly useful and powerful formalism for talking about quantum entanglement. So the basic component. So the basic. Here's a basic topological component. I've managed to draw that almost exactly over this pre-existing. So this is something that we can draw in a compact monoidal category for it to correspond to a morphism in a well-defined way. We can label it with some objects, like A, my compact monoidal category, and perhaps we should also draw some arrows on it. We want this to be an oriented one. What Samson emphasised was that we can read this as a history describing a quantum process where time in this notation moves upwards. So in early times we have no systems. Then after some particular critical time, in which some process occurs, we're left with two systems. And these two lines we have going upwards are world lines describing histories of these systems being traced through space-times in some sense. And crucially, the categorical semantics then exactly tells us that these systems have been created in an entangled bipartite state. Entangled states are well known for a very long time, very important information in quantum foundations more broadly. But what Bob and Samson showed is that the fact that entanglement can be represented in this way by the very piece of wire lets us understand very beautifully how certain quantum protocols work, and it gives us a real insight into their structure. So the most important example is quantum teleportation. So this is a picture I've drawn. This is a history describing how we might implement a quantum teleportation procedure. So down here, we have a vertical line. This represents some pre-existing quantum system. Time is going up to this before. We're now introducing two more systems over here in an entangled state. So this critical point here is where these systems have been created. And so at this time, represented by this slice, we have three entangled systems. This composite here on the left-hand side, the morphism labeled Fi star, over this cap, represents measuring the first two systems in the joint bipartite state. And the reason we have to have a morphism there, Fi star, labelled by some index I, is that measurement in quantum theory is non-deterministic. So there are various outcomes we can get, and we label these. What happens later on in the procedure is that the agent who controls this third system applies the inverse operation, Fi inverse to the Fi. So this is the description of quantum teleportation procedures, and it will be familiar to somebody from in more conventional approaches to computer science. We can now use this beautiful categorical semantics to simplify this picture to see what happens. So the first thing we can do is simply slide this initial box Fi star around this lower wire. And what that does is it applies a star. Star just means rotate. We rotated this box around. So our Fi star, star, star is a group. And now we have Fi next to Fi inverse. So these operations will cancel. And now we're left simply with a piece of bent wire. The whole point of this semantics is that one can smoothly deform the diagrams representing these morphisms without changing the identity of the morphism. So we can smoothly deform this into a straight line with no critical points. And clearly this is the diagram that simply represents the transfer of a quantum system from one point to another in a way that doesn't disturb the state. So in this way, compact monoidal gives us a beautiful way to understand why procedures such as teleportation. And it's the categorical semantics that allows us to do that. something that wasn't, I think, particularly recognised at the time, 10 years ago, was what was being done. This is actually much more broadly applicable. Exactly the same argument, but used in a relational setting, rather than a Hilbert space setting, can be used to describe, to give an account of, in almost exactly the same way, why encrypted communication by a long-time pad works correctly. So in that picture, this procedure here, which initially, from a quantum perspective, we interpreted as creating entangled quantum systems, from a non-deterministic classical perspective, we would interpret as creating shared secret, creating correlated secret private information. So, some intelligence service headquarters and some field agent getting together and preparing a code book, which they both share. And of course, important that these code books correspond and correlate to each other. This process of creating shared classical correlation is also exactly described by this compact categorical semantics. So a relational setting rather than a quantum space. Okay, well now we're going to move further along our categorical landscape. We're going to talk about Frobenius algebras. This is something else that Samson's worked on a lot, with many others in the group, such as Alex Kissinger, Ross Duncan, Dusko Pavlovich, Bob Cooker, Chris Hoynan, everybody in our group really, and many people who aren't in our group. When you start naming names, you've got to be careful, you've just got to keep going. People get angry. In fact, while I was preparing this talk, I really spent quite a lot of time, a number of hours, thinking, look, it would be nice to have initials down here representing, because there's such a concentration of expertise in this room, representing all the work people have been done, but it rapidly became clear that almost everybody has worked on almost everything in some sense, which I've written here. Then, of course, you're also guaranteed to offend almost everybody by leaving out the one thing that they thought they were. Anyway, so we're moving along now our landscape. So this cell I've labelled 2 dualizable. We'll see where it is later. But the picture I've drawn here in the middle is of something called the Frobenius algebra. And these have been used in our group to understand the behaviour of classical information in a quantum context. So classical information can be copied, can be deleted, can be compared in canonical ways. This is something that simply is not true in quantum information. So a very productive approach has been to see this as a structural resource to axiomatize it. There are various basic axioms that these copying, comparing operations must satisfy. For example, copying must be associative. We start with a single instance and we copy it twice. It shouldn't matter if we make a copy, then copy the first copy, or we make a copy and then copy the second. Natural family of simple axioms. But the most interesting axiom is this one, which is called the Frobenius axiom. So again, I'm reading these diagrams upwards, and this vertex, where one line branches into 2, represents copying, and this vertex here, where 2 lines merge into 1, represents comparing. And this is done in a sort of post-selected sense. So we should think of this comparison operation as more like verification that the 2 input wires are carrying the same data. We're post-selecting on that condition. And if it turns out that in fact those wires do not contain the same information, then the computation simply halts in whatever sense is appropriate for this model of computation. So to see why this should be true is really very simple. Let's draw a little picture on here. It's really not mysterious at all. Well, it's a beautiful observation. This is true. Let's see why. If this first wire contains classical information labelled by A and the second by B, well then when we get to this point, the first wire will carry A, the second wire A, and the third wire B. And then this first wire will still carry A at the end, and the second wire will carry A, but only if the tokens A and B are the same. So the input, general input AB, gives a general output AA, delta AB. The same is true here. AA, ABB, A delta AB. These expressions are the same because of the occurrence of this delta term. So it's simply can simply be observed that this is a property that copying and comparing operations have in classical computer science. But it's a surprising and useful insight that this is in fact a very powerful axiom. And it's an axiom that's studied a lot in that context, especially in representation theories for reasons. Now, key point here, as we proceed along our geometrical path, that the axioms of Frobenius algebra are just the same as the properties of two-dimensional surfaces. To me, this is a wonderful, deep, and surprising fact, not been sufficiently taken seriously. So let's just look what I'm doing as I switch between these pictures. This is just a change of notation on one level. Something very exciting. Whenever I have one of my copying procedures, I'm simply thickening it up and representing it by a cylinder that's splitting into two cylinders. When I have a comparing operation, I'm simply replacing it by two cylinders smoothly joined to a single cylinder. And it's of course clear that relative to their fixed boundaries, the left-hand surface and the right-hand surface are diffeomorphic. So if we interpret equality as diffeomorphism relative to the boundary, this represents a true identity between the surfaces. And in fact it's the case that this gives a complete way to account for the commutative between the samples. One can, in a very straightforward way, set up correspondence between diagrams of this form, drawn using these vertices, the diagram of this form, drawn using surfaces, and the two equations will hold in this style under the axioms of Frobenius algebra if and only if the corresponding surfaces. Now this is something that the topologists, of which I'm glad to see we've got this one is in the room with us, have been studying these things for a long time, quite independently of the relevance of Frobenius algebras in science. And in fact there's been an explosion of work in the past few years on these sorts of topics, on the way that we understand mathematics now, thanks to the work of somebody called Jacob Lurie, who proved this beautiful conjecture by John Bayes and James Derlin about a categorical structure, a beautiful, simple categorical structure that lets us understand categories of manifolds in a very general, very simple, very powerful way. That's something I don't go into here, but it's sort of nice that these structures that are proving important for us are also in some sense at the cutting edge of work in modern algebraic topology and representation theory. And they have a snappy name for these, for the categorical semantics that lets us draw these surfaces and simply interpret them as morphisms in a categorical sense. And the name of this structure is two-dualizability. It's a convenient tag for me to use here. And compact categories contain one-dualizable structures. So I could use that notation. Now, so what I've been doing along with some collaborators is to show how we can combine these pictures. So we can allow ourselves to draw surfaces that are going to represent classical information, and lines that are going to allow us to talk about entangled quantum systems. We can draw composite graphs in this sort of higher geometrical logic that give us single geometrical expressions of useful procedures. So I haven't got time to go into the details, but this equation, for example, represents correctness of quantum teleportation. M is a measurement procedure. So here are my lines are quantum, my surfaces are classical for the reasons we can see. Then what are the things that are happening here? Here I'm creating entanglement, we saw that earlier. M is a procedure that turns quantum lines into a classical surface. So it's a measurement, in other words, that's what measurement is. And U is something that has a quantum input and a quantum output, so it's an operation on the quantum system, but it puts in the context of this classical information system. So it's an appropriate representation of a controlled operation. Where I'm going to do something to my system I have locally. My choice of what I do is to depend on some generally available background information. And this is a completely different way, a completely different sort of empirical semantics to represent representation, different to what we saw before, which looked entirely at the compact part. On the right-hand side, this diagram represents success of the teleportation procedure. So the equality represents correctness of the entire thing. I nice thing about this framework then is that solutions to this equation in two hills, so natural monoidal two category, which to express this sort of these sort of high dimensional models. Solutions to this equation exactly one-to-one correspondence with actual lab implementations of quantum teleportation. So if your favourite physicist comes over and says, I can do quantum teleportation, this is the measurement I do, this is the entangled state I create, this is the control operation I do, you can use that to immediately build these components. And the procedure that he or she has described to you will indeed work in their lab if and only if these components you build satisfy this equation. But it doesn't this formalism doesn't only give us semantics for quantum ideas, also for classical non-deterministic ideas. So you can also describe classical encrypted communication using this picture. Now our interpretation is different. Instead of quantum and classical data represented by two-dimensional parts, we have private and public information. And we can interpret these parts in a slightly different way. This critical point here, which we previously interpreted as creating an entangled pair, we now interpret as creating a one-time pad, creating shared classical correlation. This M now corresponds to a classical encryption process, and this U now corresponds to the encryption process. Again, we find that solutions to this equation in an appropriate bicategory, which I call 2rel, which is essentially a profunctor category, for those of you who know about these things, valued over a rel, set. Solutions to this equation in that setting again exactly correspond to correct implementation of encrypted communication procedures. That would be a particular choice of the one-time pads that you might create. The encryption procedure might use the decryption procedure. And you can also analyze the security properties of this procedure and this setting. So you can show, for example, that if you encrypt and then you throw away the remaining one-time pad, the original message has been lost. But of course, now we started on this path. So what happens if we go to 3 dualizability? Well, still we have beautiful connections too. In fact, even existing work in science can also, of course, to quantum computation. So we now have an extra dimension. This means that our surfaces, lines, and vertices now live inside regions that themselves are labels. And I suppose the briefest thing to say is that these regions are effectively labelled by theories of particle physics. Okay? And our lines are not quantum systems in the abstract, but they're fully fledged quantum particles in this theory of quantum physics. And so a diagram like this, where all we've done is taken our teleportation diagram, drawn these labelled volumes around it, now represents schemes for teleporting quantum particles in some richer sort of quantum information theory that's been instantiated inside some theory of particle physics. And these have been very little studied, so that's an example of the sort of application there is in this work. And it also connects very interestingly to notions of braided linear logic and these categories across G-sets, which have been important in the development of trace model. And many people have worked on these things. Masahito Hasegawa has got some interesting recent work. Very closely connected to these. So what if we keep going? Well, this is as far as I'm going to go because I've run out of space on my slide. If we go to 4 dualizable structures, we reach topological string theory. So the diagrams that we draw now are no longer particles interacting, but they're particles and strings interacting. This is generic string theory pornography picture that I scraped from Google Images. This is a picture on the slide. But the point is we can use the same approach, the same information theoretical computation approach. And this, because of how the genuine sense in which all these areas are connected, this really does give us an opportunity to analyse, I think, the logical concept of string theory, ask questions such as what algorithms of strings perform. Can we teleport strings, for example? Can we apply the basic notions of quantum information in this context? It's completely unexplored, but very natural from the perspective of semantics. Okay, so just say a few more things. There are plenty of interactions between these different boxes, these different parts of the landscape. So something that's very well studied is an exponential comonad, which lives in linear logic settings in certain nice cases. And these turn are linear.
You shouldn't really write that as an office object. That's not quite right. Linear logic.
Depends how I've defined my plus and my times. This is supposed to be very high level and generic, right? Because different this is morally the structure of an exponential pronoun. And it's well understood that these can give back to closed theories from linear or quantum theory. Also Samson's work in this area has been on linked construction, which goes downwards as a trace quantum. We can also use rel constructions to move downwards. There's all sorts of interesting things, and of course here I'm just touching the surface. And all of these areas, there are many rich interactions. Also, there's a trace operation you can do on the bottom. So, at each level, for each n, we're drawing n-dimensional manifolds. But you can always look these n-dimensional manifolds up, step very far away, and they look like n-1 dimensional manifolds. For example, if I look at a surface like this, it looks very two-dimensional. But if I loop it up on itself, like this, and then you step very, very far away, it's going to just look like a line. The effective dimension reduced. This gives us a way to step down. So there's a rich family of interactions between this landscape. These are very far from being isolated facets of understanding. I think these interactions should be something that should be thought of in a whole lot more. Okay, so what's clear here, what's really supposed to be the punchline of this talk, is that these lie along two axes in a natural sense. The vertical axis, which can be thought of as increasingly geometrical as we go downwards, Cartesian traced compound. And as we go from left to right, increasingly layered, increasingly high dimensions. So when we go from left to right, this gives us the opportunity to have different types of structure coexisting. So our categories become two categories. So something that's very interesting for me is to ask how this landscape extends. What should these missing logics describe? It's easy to say, oh, I can come up with a Cartesian 3 category, or I can build a 4 category that looks a bit like a transform or something. But that's, and certainly there is work that one can point to in the mathematical literature, also in the computer science literature, certainly in mathematics and the computer science literature, and the category theory literature, that is like we're sort of firing a shotgun at this picture, right, and filling in certain points. But I think it's really quite clear now what sort of logics we're describing here, and also we understand them because we know what they're good for. We prove them, what sort of scenarios they're equipped to reason about. Here, I think, there's a big gap. What's particularly interesting, I think, is that we have two completely independent ways to talk about classical information here. As we go upwards, say, using an exponential comonad, a linear setting, a Cartesian setting, we reproduce classical logic in an infinitary sense, in the sense that this exponential comonad corresponds to an arbitrarily large number of copies of our limited resource. Whereas as we go on the horizontal direction, say, this Frobenius algebra is inherently finite dimensional, but do nonetheless have classical properties. So it seems maybe in some sense what we have here is two different notions of linear versus of resource sensitive versus resource insensitive, which are expressing themselves in these different ways, and which really, as we approach these other parts of the landscape, should come together in their relationships, will be understood. And in fact, something that always bowls me over when I think about this is that, how many of you know about this stuff, but in the foundations of quantum physics, the single biggest open problem, in such a deep and profound way, peristaltic, as my old supervisor would say, is how our classical reality emerges from what we know to be the quantum foundations. And something that's used a lot in this literature is something called Fock space, which actually has exactly the same structure as this linear exponential comonad. So the single big open problem in our understanding of quantum theory today is how classical structures emerge from quantum structures. Isn't this what classical categorical logic is? Isn't this what this community has been doing in some sense for so many decades? And I think there could be real answers to those questions. This particular question from physics, for example, by really taking this landscape seriously and understanding it. So what are the implications more broadly for programming languages? And don't forget, key takeaway string theory is a
maybe I should mention that, I mean, of course, when you draw a landscape, you don't exactly know how things are connected, and the fun of research is to see unexpected valleys. So about 10 years ago, Day and Street showed that linear logic is related to Frobenius algebra. So I will speak about it this afternoon, but I would be interested to know if you have this in your panorama.
Sounds great. But I mean, of course, I don't claim any sort of comprehensiveness of my description here. Quite the opposite. I've deliberately been. So of course, there are many other things going on here. But, what you're saying reinforces my argument, I think.
Yeah, sure. I think we don't really understand the dualities, I mean, how the dualities of logic are related to the dualities of geometry.
Right.
And so this is exactly what you're saying.
More questions? Yes.
So I was wondering where anions fit in this picture.
Well, I drew a picture of them, in fact, didn't I? So here. So these are lines now. They're quantum systems, but they're now living in some background. So they are, in fact, anions. So if we have a solution to this equation, we have a way to teleport anions. And there's no such procedure in the literature. In a very similar way, and we'll talk about this, but we could draw a picture that represents dense coding anions, or complementary pairs of anions. We could apply, using a lot of the formulas that we've developed in our group, a lot of traditional ideas from science in these interesting contexts using these topological ideas. It's completely unknown how that comes out.
But it's the way you were talking about it originally, it seemed like these were ordinary particles that are in 3 dimensions.
These are, everything here is topological. I don't keep saying it everywhere because it gets tiring. So this generalizability is all about topological structures. So these are topological problems. Those are topological problems.
Okay. Samson?
Well, you made a very interesting, you raised a very interesting point with me and Jamie about the fact that there are these two different perspectives on classical information, sort of Cartesian one up at the top left, and then the sort of, I think one gets from Frobenius algebra progressing along. So I just have a sort of a thought that somehow in the way that you as you've shown us in these high-dimensional diagrams, the way we're thinking of the classical information is that all the branches are carried along, as it were, together. So it could be related to a sort of, quote, multiverse view of things, where the choices are not resolved, and there's no particular projection postulate. And that's somehow the flavour. I mean, I think that's in some broad sense that's the flavour of it. Whereas, of course, if you go to the usual way of handling classical information, you actually have projections, because it looks like a pun, but you have the projection postulate because you have projections and you explicitly resolve choices. But I wonder if that isn't the
Yes, so perhaps we have here in our hands precisely one of the other fundamental arguments at the heart of theory, which is how we should interpret it. Yes. So it makes it particularly interesting then to proceed to the unfilled part of the diagram where perhaps these things will be brought together somehow.
So on that sort of theme, when you showed the teleportation with the surface to the classical information, have you done analysed protocols where you've got a cap where you forget classical information?
Yes, that's very nice. So you can describe, for example, these quantum erasure experiments where you do a quantum measurement, but then